squeezed it all the way down. I dropped in 3 pages to, where was it, 3,000, from 12,000 to 3,000. Wiped it out, huh? Maybe something's finishing here too. So that's what's really taking over. When you get into bigger systems, VHAND doesn't do much. These are going to stop at 100 megabytes in free pages. That's a lot of people are just seeing, you know, why am I getting swapping when I have memory free? They all interact. That's the hard part.
I'll give you 3.
Thanks. So far, the main problems I've had were all miser related. That bug, by the way, I've had filed for 4 years now. Somebody was going to be fixing it a month ago and they still haven't fixed it.
You would think being able to show our customers that things are working right would be higher up on the priority scale.
Behaviors are hard to test. Testing processes are automated. They test for reliability, they don't test for behavior. And when codes are changing, this kind of stuff does change. And then with developers going through the code, new developer every couple of months.
Yeah.
And they all look at something different. We're just looking at how these are behaving. They're just looking at their little niche of code saying, how can I optimize this piece of code? And then the behaviors change. Or there are a lot of trade-offs where one person doesn't like the kernel being too big, so they want to release it right away. When other people say, but I've got good data in the kernel, I want the data there. So at this point is when I'm just throwing the IO load at the problem, then the memory load at the problem, and see who wins and try to adjust the partitioning, the abuse that's going on. And meanwhile, at this point, if I were successfully working, I'd still have code 2 in the mix, surviving everything without any impact. That's the intent of the class. Plus, if I still had fair share, then I'd have CPU wait time. Pick one person that would run timeshare with fair shares and watch them get through before everyone else.
Oh, what did you play with to do that?
Do what?
All of it.
F3. Free C.
No, green.
This year? Well, I killed the load and everything came back here. Did you just mark the tapes with numbers or subject to?
Numbers.
Okay. So what I was going to do is take them home, and scan them in, and then send you CDs.
Wednesday.
There is a certification testing plant going on. We're supposed to, like, March or April next year, be in full place with that. I've got to write 50 questions for this class. I've kind of marked the tools and the subjects, but I haven't formed the questions yet.
That would be interesting to
Yeah,
see.
it's kind of hard to test on. Is it running now?
Yeah, go to my certain
Or,
Sí, porque lo que pasa es que sabes que hay un plan
Of
de
course, the
certificación
queue
para
says
seguir
it's
ese
there.
gráfico que ya está ahí. A nosotros por lo menos nos van a
Yeah,
mandar
go
correo
to
electrónico
MP
que
Miser.
quiere tomar un examen
That's it, it's in the
porque
queue.
lo están haciendo, ¿sabes?
Ah, pero es nuevo eso.
Nope,
Sí,
no job
entonces
submitted.
ahora por cada clase que tú tomas, seguramente tienes que tomar un examen sobre la clase.
Barfed on this one.
Ah,
Sí.
Since I was supposed to be checking out what you're saying.
Oh, you're recording right now?
Yeah.
Oh, okay. We're not saying, we're talking about the certification that he's asking me what kind of state that's asking Dave about because he's not aware of, and I said that's probably, in the next few months for every class you take, you have to take
Mile
a test,
return, ground
to
zero.
see if you really learn or not.
I just felt like you should be aware of the fact that I was recorded, but what you were saying was your business.
There.
Yeah, it's the,
Is that
Problems are not logging.
test is gonna be after you take the class, right after you take the class, it's gonna be like or it's gonna be right after? That's gonna be hard,
Very.
Yeah, because because like for me, I have too much information on my head right now, I probably need like go home, take the book, reread it again to put all the pieces together, and then probably I will be able to take a test. And it put, I think, a lot of pressure on the person.
Yeah, I'm with you. I need study time after a class. I guess.
Yeah, I can, it's, for those people who are fast learners, that they can pick it up stuff really fast, it's okay. Or at least you already have a lot of experience in the training you're taking. So, because this happened to me, like, I took the grade class just a few months, 1 month ago, and it was really easy because I have to learn by myself. I have taken too many cases related to grade as I have been forced to study, to answer questions. So when I took the class, I was just filling up forms, as I have. So in that case, if they give me a test, I will be able to probably answer all the questions. But in this case, where I am in the process of learning everything.
By the way, on the system right now, I changed min file pages, and the cache is larger than it was before. Before break, I was changing min free pages. Now I changed min file pages and made it a lot larger, and now my cache is much bigger. I still have that bug going on. I'll be right back in a minute.
¿Cuánto van a hacer esos test?
Those tests are going to be like, he said April.
Del año que viene.
Sí, él dice en abril, abril del año que viene. ¿Sabes?
Ah. Al final de cada clase va a haber una prueba.
Él dice que él tiene que escribir 50 preguntas para esta clase.
Sí.
Eso va a ser dificilísimo, ¿sabes?
No, pero a mí me parece bien, porque si no es una joda, venís hasta acá, lees, no te genera ninguna presión.
Sí, es posible.
A mí me hubiera gustado que tomen una evaluación.
Lo que pasa es que yo creo que en ese caso hay como que muchas cosas envueltas, porque a mí por lo menos me ha pasado que yo voy a clases donde no me gusta el profesor.
Ah, bueno, sí.
Hay profesores
Que se van.
que son muy desorganizados. Entonces, un día, ¿sabes? Los 2 primeros días van burda de lento y después se dan cuenta que no están con el horario y entonces los últimos 2 días te quieren meter todo a costa de lo que sea. Que fue lo que le pasó a este pendejo. Y viste ayer cómo iba.
Sí.
Ayer iba rapidísimo, que yo no podía ni siquiera escribir nada de lo que estaba haciendo. Entonces, eso es otro problema. Lo otro es que por lo menos hay clases que a mí a veces no me da tiempo de hacer un laboratorio. O sea, y sobre todo si ellos están en el horario, cuando empiezan a presionar y ya te dan el primer tiempo para los laboratorios, eso no da tiempo de hacerlo. Entonces, no sé, pienso que el examen debería de ser opcional para quien lo quisiera tomar.
Claro.
Y en mi opinión debería de ser una semana después de que tú tomes el curso, una página de internet que tú vayas y tomes tu examen. Eso es, yo en eso sí estaría de acuerdo. Entonces tú a la semana
Claro, bueno,
te
eso
puedes
sí.
llevar tus
Sí.
libros a tu casa, repasar todo lo que hiciste y después ir a internet y responder tu examen. Y si lo pasas bien, si no, no lo pasas.
Claro, no, es verdad.
Porque sabes que no todo el mundo tiene la misma rapidez de aprendizaje. Hay gente que a lo mejor se puede sentar en un salón de clase y memorizar y aprender y captar todo lo que la persona dice. Mientras que hay otras que no. Hay otras personas que necesitan ver, tomar información y después repasar para poder entender. Yo por lo menos soy así, yo estoy en clase y yo entiendo en general lo que está pasando, pero yo tengo que ir a mi casa otra vez y
Sí,
leer.
seguro. Sí, seguro.
¿Ves?
Aparte,
Entonces,
hay un montón de cosas que hay que configurarle a esto como para hacerlo, ponele, para verlo bien. No sé, yo me llevo todos los códigos, ya los tengo copiados en mi máquina. La máquina de allá ya me lo copié todo. Y agarro una máquina multiprocesamiento, lo pongo, lo pruebo tranquilo y miro todo más tranquilo. Porque hay muchos detalles que él los da como por sabidos, tipo, no sé, agarra el NQE y dice, bueno, NQE, QSUB, tanto puesto por lo otro, y no, y hay que ver bien a ver qué es lo que hace cada uno. Pero no sé, por ahí son detalles que si uno trabaja todo el día ya lo sabe, pero si no lo viste nunca.
exacto.
Bueno. Pero no, sí, yo pienso que tendría que haber un test. El de la web me pareció bueno, igual que los de los compacts, que después tenés que dar el examen en la web. Los CBT, los scores CBT.
Here's a report of all your jobs.
Pero bueno.
Actually, it was a 13-page report, I only printed the beginning and the end of the report.
Okay.
Those codes that you give us to run, did you always have those codes in view?
Yeah,
Oh, they're always over there? Okay. It's because, once I would copy them, but if they're always in view, I
Yeah.
wouldn't bother because
Oh, that's
I have
fine.
access to that system.
yeah.
Okay.
I just like them because each of them has a way I can stress the system without hurting anything else.
Right, okay.
You got a permission denied on yours or something. Everything else looks like it's okay. So is it permissions in here?
Process. Where's the other permission denied?
This I just don't feel like permission right there.
Does it show the queue that's, no, you have to
He was
use.
this, so here's what I was, that's what was given. So the only thing I figured has to be careful.
Well, I was thinking that when I created the test, I thought that everybody could submit to it, but NQS might not be able to.
Oh.
But I'm gonna have to leave that alone right now.
Okay,
What I just passed out was a sample report coming out of the the CSA accounting package. I unfortunately didn't print the headers. So I've been running accounting all week, and it was actually a 13-page report. I just gave you a sample of it. You go find it here. there's a command in the CSA packet called CSA DREP. And CSA DREP is going to take all my NQS jobs and then give me an NQS report. Unfortunately, I didn't print it with a header, so I needed the -H option. And the -B verbose for. So far this week, we've run 5,484 jobs. I'm sorry, that was interactive. We logged in and logged out, as well as cron events and stuff like that. Came out to 5,484 sessions. In terms of NQS, we've run 759 jobs. And in terms of CPU utilization, interactive is so far has used about 60% of our resources, and NQS has used 40%. So this is the total number of seconds that I have in my report so far. And as an accounting person, I would compare that to what I had for the whole week, for example, since I'm looking at a week's worth of data, but we weren't running 24 hours a day, 7 days a week. And then for each queue, I've got the header actually added into this report. So for each queue, we then have a job record for the entire job, every queue sub that we've done. So we get username, job name, here's my CPU time, memory sizes for physical memory and virtual memory, I/O wait time, here's the VIO wait time instead of the buff I/O wait time, and CPU wait time, and then system time. And the number of bytes read, number of bytes written. Now, up till now, we've been looking at it on a per process basis when I went into accounting data. This is now consolidated the whole job, the compile, the link, the run, JA, everything into a single report. You've got byte written, bytes read, logical reads, logical writes, blocks transferred to disk. That's where we need to finish off right now, by the way. And then queue wait time, how long I waited in the queue, what queue I was in, elapsed time, start time, stop time, and starts and stops are by date, and then time. And then there are the ability with the verbose option going on to the top program names and stuff like that. I don't have them printed here. So there's a whole bunch of metrics that I can get out of the CSA DREP, but I don't have a tool to actually plot it yet like SPV gives me. Now there is one last piece before we talk about the memory chapter, and that was SAR-B. So on your login to do, and just type in a SAR-B, let's take a look at it. We're going to take a look at the head. And I'm also going to go under SPV and just plot the cache I/O one. So this is the one slide that I skipped over in the last chapter before we go on to the memory chapter. And we've already discussed this. We have logical reads is what the kernel is being presented. So every time I do a read or write system call, I count it. Okay, in a printf, I may have a whole bunch of printfs that fill this library buffer, and eventually the library buffer fills up, and then we make the system call. So if I increase the size of the library buffer, I reduce the number of system calls. If I'm doing a terabyte of data 1 byte at a time, I might want to increase the library buffer, pull more data in at a time, okay. And then I don't have to make as many system calls, which means my system call time goes down. I'm not in the kernel as much. This is one advantage on an NFS server. If you're moving large files, to start upping the size of these things so you don't do lots of little pieces. You know, if I try to put out a fire, I don't want to put a little bucket out. I want to make it a big bucket. If I don't want it too big, I need to be able to carry it. Okay. So logical reads and logical writes are what are presented to the system. Coming out of the back end of the cache is B reads and B writes. These are what are going off to disk. Now they actually get queued up by the device managers. And then P reads and P writes are what are going to disk, bypassing buffer cache. So on SAR-B, here's my request to disk, here's my logical request. It's good when I do 69 requests, or let me do 42 here, and I did not have to go to disk for any of those requests. The data was in my buffer cache, which means I got a 100% hit rate. I found all the data 100% of the time. Meanwhile, on my writes, it did a logical write 202 times, and only 32 times did that stuff flush to disk because of BD flush. So I could do a write here and not see it for 10 seconds. We were looking at the memory growth and shrink, but we weren't actually looking at the logical reads and writes as they were growing. So there they are, B read, L read, B write, L write, and P read and P write. Now I'm just going to check something here. I've plotted that chart, and I just want to see if I have any direct I/O. And basically all week, except for one event, we have not done any I/O bypassing cache. All I/O this week has been through buffer cache. Okay, if I add a swap file, that will change. If I start using a sign command or doing file system backups, that will change. There's been no direct I/O bypassing buffer cache. The other metric that was on this list is write cancels. A write cancel says I wrote to cache, read it, modified it, wrote it back, but the 10-second flush had not occurred yet, so I'm going to cancel the write. So if there's a write that has to be overridden, so to speak, that's called a write cancel. If I'm on a database server where maybe I'm reading, writing before I flush it to disk, I might want to slow down auto up to give that data a better chance of staying in memory. That way I don't have to flush it to disk, bring it back, and modify it again and sit there thrashing to disk. If I'm constantly changing it, let's keep it where it is. The last two metrics on these lines are my hit rates. %R cache and %W cache. These are computed as L read minus B read over L read times 100. That's what we call a cache hit rate. Now there is another metric that I endorse that's not on this, but is useful, called a ratio. And the ratio is L read over B read. So a good ratio, L reads are going up, B reads are not. The same thing here. A good hit rate, L reads are going up, B reads are not. Meaning that as L reads go up, my hit rate is going up, as long as B reads aren't occurring. Now, in my opinion, you can increase NBUF and not have the hit rate any better, because it's normalizing the activity. I consider hit rates to be more in abuse of the system. If I increase NBUFs, that gives me more buffers to abuse, and my hit rate may not look any better, even though my I/O wait times are better, because there's more buffers for me to get. So you could have the scenario where somebody says, I got a bad hit rate, let's increase NBUF. They do it, and the hit rate doesn't change. The I/O wait times might, though. The bottleneck, the number of code 3s I can run at one time might change. The other thing that changes, though, is the ratio. And I like to call the ratio the reuse metric. So it's possible for my hit rate to still be bad, but my reuse to go up, because I'm doing a lot more logical requests than I did before. So I can increase NBUF, not have the hit rate get any better, but get the ratio better. Now, that's the purpose of a cache, is to hold my data close to my program. So now you've got to decide in your scenario, am I reading more than writing? If I'm reading more than writing, I want this to be my hot path. I don't want stuff going off to disk. And particularly for latency. Or if it's bandwidth, then I'm going to bypass buffer cache and get straight to disk. So in the video market, media-based, we'd like to do direct I/O. So this is for latency, this is for bandwidth. Now, a good cache should have the traffic going to cache but nothing to disk. Okay. I have had cases, for example, I was reading a file, it didn't fit into cache, and the news server was toggling between these two files. So we'd read in all the inodes, we'd read in the file. When we read in the file, all the inodes would get squeezed out. In other words, in this scenario, my hit rate was negative, and I had more physical disk traffic than I had logical. In fact, let's see if we can find any here. We increased nbuff, so it wasn't too bad. This one got fairly close. I did not get what I call an upside-down cache. An upside-down cache would be negative, where physicals are higher than logicals. Okay? Now, several ways that that could occur. The first one was cache too small. So going through our cache behaviors, there is, again, a cache bust situation where the file larger than the cache. So when I logged into this news server, the inodes were as big as what nbuff was set, and then the file was as big as what nbuff said, and you'd see the two thrash. So in this scenario, your B reads were greater than your L reads. The other thing that can cause this is cache fragmentation. And one of the things to watch out for here is auto mounts. NFS servers have this problem too. If I am auto mounting a file system, that's for convenience. The trouble is that all the metadata for that file system is allocated in buffer cache wherever it finds a space at the time of the auto mount. You want to move those things. This is bad. You want to move them into FS tab and mount on boot. So if I've got lots of people logging in and then they get these auto mounts occurring on the fly, eventually I'm going to have these super blocks allocated all throughout my buffer cache. And there's no garbage collection in buffer cache. Now if I unmount them, those buffers then get released. But I could have a big buffer pool, for example, and I started allocating buffers for all my boot process. Then a user comes along and allocates buffers for a file, and then I come along and mount a file system. All that mount table information might be there. Then this person releases their file, they're done with it. Then somebody else comes along and makes a file, and then somebody else does an auto mount. Then this person releases this file. Somebody else tries to get a file, and now they've got a fragmentation problem because those mount points are allocated. The metadata for those file systems are allocated at the time whatever's available in the buffer header chain. Now the only way you can see this is with buff view. Because buff view will show you all the metadata information and the actual buffer number where they're located. So in both those situations, I could have physical higher than logical. This would often occur on a Cray Unicode machine because the cache couldn't grow and shrink. It didn't have any breathing room. IRIX does better having that breathing room. So eventually, after 15, 20 auto mounts, you got all this super block information scattered throughout your cache, and now you can't get contiguous pieces for your files. Now you start squeezing more stuff out of cache to find room for what you're getting to. So in those scenarios, your hot path becomes physical or higher than logical, and your hit rate actually goes negative. Now I only went to 4% here, but if this had been like 230 instead of 136, I would have had a negative cache behavior. Now some of the tools just stop at 0, but OS view, for example, shows it negative. It would actually show negative hit rates. So when you get negative hit rates, that means your physical is higher than your logical. Now I'm just going to look at the data that I've got here. So write requests were occurring. Write cancels, 200-300 at a time. Code 3 is doing random I/O with LSeeks, and there are write cancels associated with Code 3 runs. These are the number of disks requests. So these are the B reads and B writes going off to disk. And look, I'm reading more than writing, but not much. And remember, Code 3 wrote more than read. We didn't keep it there, but we had it up earlier. Again, these are quiet parts where a different route was running. We don't have data available between the days. And then here's my logical reads and logical writes. Here now we can also see the reds are higher than the blues. There are a couple of places where I'm writing more than reading, but in terms of logical number of calls, my reads are higher than my writes. But the amount of data moved, the writes were higher than the reads. So I was doing large writes and small reads. So this then just takes the write request, logical and physical. So here's a good example where I had a burst of logical, but there was very few physical requests going on. Okay, right in here, the difference between the two. So I had a burst there, the logicals went up to 250,000, and I only had to go to disk 800 times, or 8,000 times, out of the 250,000. Whereas over here, this one looks like a bad one, 40,000, and I had to go to disk 15,000 times. Okay. So every logical has to have a physical. And then here's my read requests. Look at right in here was rather bad. That was when we had a very, very small cache. So here I'm doing 15,000. I had to go to disk 18 versus 10. Looks like I had to do 18 logical and go to disk 10,000 times. This one right in here looked real bad in terms of my reads. Okay. So it's a different way of looking at the data. Now I can start to see some of my cache ratios. The fact that I upped nbuff was like Wednesday right in here. I now have been able to throw IO loads at the system and get a very, very high cache ratio. The higher the ratio, the better. So I'm getting a 5,000 or 6,000 burst on my reads, but writes are not going to be that good because every write has to have physical I/O. So my write ratios were more on the order of 100 to 300. And then in terms of hit rates, look at what our hit rate was doing now. So here's 100%, and even though we were throwing loads at the system, this is probably non-prime time, nothing running, yet we still had hit rates dropping down to about 95 or something like that. But here's what we've been experiencing today as we try to create these two loads. And again, there were 1, 2, 3, 4 times that I got very, very bad cache read hit rates. Also, you can see some of the writes going on. It's possible that after a write, when you then do a read, you can't find any of the read data, and then you see right after a write a read miss where the read hit rate drops. Even right in here, you can see both the writes and the reads were rather heavy. Now, generally, what people say is they want to have the write. By the way, you can see, let's see, is that the whole week? Can't see it a whole lot. Let's see the first day. We weren't here that day, the 16th. Here's what we look like on the first day. And our hit rates, a lot of times, were below 87%. Let me even just try to get this a little bit better here. I'm trying to see the nbuff increase. So here were times where we were getting in the 15 or 20% cache hit rates. And then later in the week, where we are right now, we're still in that same range, even though I've upped nbuffs. But we haven't looked at how many concurrent copies of Code 3 can run at the same time. Now, there was one other parameter or tool that we needed to talk about in this area, and that was par-k. So Warren, do you want to run some par-k? Or I'm sorry, some code 3s? Par-k is what's coming out of the back end of the cache. Oops. I have to start the RT-mon beam. Turn it off to see if the miser would run better, but it didn't. R-K. Note that there's nothing happening right now because buffer cache is not pressured. There's no physical IOs going on right now. So, fire mouse on, there we go. So all those physical IOs are being clocked here by the par command. So this is what the B reads and B writes are, what's being presented to the volume manager. I'm going to have to break out of this so that I don't keep getting data. Par-k, put it into a file, par-k file. Just let it run for a few minutes. So taking one of these records, this is the time since I started par, the CPU that I'm on, the process or the kernel thread. Since it's a big number, this is a PID or a kernel ID, whereas this one is in user space for cron doing something. And this one happens to be a kernel interrupt handler. So we've got program name or kernel thread name, PID or kernel thread ID, and then for each one of these things we've got it queued up, started, and you should be able to see the done. Now here's a done, but again, there's going to be a done further down from what that B deflection occurred. So when we queued it, started, and done, after that we then got flags, which says how I opened it and a few other things. Was I doing direct I/O and stuff? Then we've got the logical device number, major minor device number. That could get converted to the actual physical disk drive, or I should say physical file system, and then we have to convert that into the physical disk drive by using a volume manager. Because here's our size of the I/O request that I've been talking about. And lastly then, this is the block number where I'm actually positioning. Where in that file system am I going? So if I was a striped or concatenated file system, that block number would have to be converted into a physical disk drive location. That's the logical block number in that file system. So it'd be nice to actually be able to plot this stuff, grab these numbers and see what, on a per disk basis, what my head movement and what my block number schemes look like. So you could actually see head movement, find a program like find, just going through the file system or something like that. Am I sequentially striding? Those sorts of questions. So we've talked about this friendly I/O buffer size. And I said 64 KB was the default. If you're doing lots of little I/O, you want to drop it down. If you're doing large sequential I/O, you want to make it larger. Now historically, people have always asked, how do I set these buffers? So I'm just going to go over here. It all depends upon whether I'm reading or I'm writing. If I'm reading more than writing, I want to make it a cache behavior. If I'm writing more than reading, I want to make it a buffer behavior. Now initially, a long time ago, before we had caches, the buffer was sized to the disk geometry. So we figure out how many sectors per track, how many tracks per cylinder, and make our I/O request big enough to fill up a rotation. So we set up our buffers to be sized to whatever a sector was, or a track was, or even cylinders. There are applications that just hold enough data to fill a whole cylinder as the heads go by. Then people started getting into caches. So historically, the second thing was the cache page size was to the disk geometry. Now remember, a buffer and a cache are two different things. Buffers are really for writes more than reads, whereas caches are for reads and reuse. So there were two things that happened. And Don Lee was one of those people that made me change how I was looking at this whole situation. Number one was we started getting zone bit drives. How do I set a buffer to be friendly to a disk drive that has different geometries depending upon where I am on the platter? And nowadays we even have caches between the disk, and it has its own geometry behavior. The second thing that Don Lee was telling me was, wait a second though, why are we setting these page sizes? This goes back to LD cache days. Why do I set them to the 48 blocks to a sector on our old DD disk drives? Particularly since in a reuse pattern, my hot path should be application to buffer cache, not buffer cache to disk. So if I'm writing, it makes sense to make these things the size of the disk geometry. But if I'm reading, I want to match it to the application. So I want to be efficient in matching these buffer sizes. So because of zone bit drives, and because of reuse characteristics versus writing, we started setting the cache page size to the application request size. Rather than to the disk geometry. Fourth thing that came along, the problem with this buffer cache, I guess that's enough of a PA bomb. The problem with this buffer cache is it's a public pool. Anybody can come along and take all the buffers. So if I write a whole bunch of data in there and then go back to try to read the data, there's no guarantee that the data is going to be there. So what they did next was user cache. Started caching within the program. And for example, in the Fortran world, we use the assign command, and there is a user cache, and there's both synchronous and asynchronous user cache and the user A layer that turned the buffer. Remember I said this was a buffer? Okay, it's chunking my data. The assign command can change that from a buffer to a cache. Now buffers do not have age information in them. Caches do. Okay. Now if I'm writing more than reading, I don't want to write into a cache because I have to maintain the overhead of keeping track of the ages, when in fact I may never read the data again. So the concept here was to get it away from, therefore it's a private. Nobody else can pollute it. The disadvantage is it takes more memory for my program. And in particular, these user cache layers were written for the auto industry for Patran and Nastran and stuff like that to do large sequential I/O and to cache it in memory rather than putting it into a public cache. Nowadays, what everyone is doing is negotiate. With STAT and FCNTL, we can ping the OS and say, what are you configured for? Okay, so the stat command has an interface to XFS, and based upon the file system I'm in, I say, you tell me what request size you consider friendly. And the default would kick back 64 megabyte, and then I say, oh, I don't like that. I can negotiate with FCNTL and change it. Go up to 128 megabytes or something like that. Or drop it down to 4K byte. Okay? So I want these flare bucket brigades to be a whole friendly number, but the common denominator is either the disk geometry or the request size. If I'm writing more than reading, it's the disk geometry I'm concerned about. If I'm reading more than writing, it's the request size I'm concerned about. But the newer applications will negotiate it and figure it out on its own. It says, I got to move a terabyte of data. I don't like you being at a 16K byte transfer size. You up your to me. Now also, we have FS tab. So I can change the operating system's knowledge of what it considers a friendly I/O request. That's the whole story here, friendly I/O. What is friendly I/O in my system? So with FS tab, we have some new parameters added in 6.5. And these were designed mostly for the RAID and for the, what's I going to say, it's taking a while here, for RAID and for the database market. So one of the parameters added to tell the operating system, don't use 64 KB as a default, drop it down, is BIO size. So I said that these buffers by default were 64 KB. That was just a starting default beginning number. But with BIO size, when I mount it, I can say the default preferred IO size is 64K. The BIO option can be used to decrease the preferred IO size. This is for the database market. So if I'm doing online credit card transactions, I don't want to waste a 64 KB memory footprint to hold a 4 KB transfer. I'd rather up the transfer size, but if it's a credit card transaction, there's nothing more to put into the data. The size is expressed as powers of 2. And basically, you can go 64, 16, or 64, 32, 16. And on 4 KB smaller 32-bit machines, you can go to 8. So with BIO size, you can get 64, 32, 16, and possibly 8 on a 32-bit kernel. So in the database market, I can drop it down with 16 KB on a typical origin. And then I can get 4 times the number of buffers in the same memory footprint. So it makes me more efficient at how I use my memory. And if I've got users that are sitting in directories that are writing simple hello mom or doing development in C where typical files are a couple thousand bytes or less, I may want to drop the BIO size down for those types of markets. Even the news server market, they will often change BIO size. NFS market. What's the default request size for NFS? The R size and the B size set it when you mount it, but 32 KB is pretty common these days. Okay, so in that scenario, 32 KB might be a better size to set if I have an NFS server. Unless I've upped R size or W size or downed it, I want to match that to whatever the R size and W size are with the mount table as I mount it. So this is just friendly I/O, whole friendly numbers, finding the common denominator. Now there's also, we were looking at the other day, S unit and S width. Okay. With a RAID cabinet, I don't know what the geometry is, so this gives this geometry information to the OS. And then XFS can be smarter about how it forms its request friendly to that particular disk drive. So when I buy a RAID cabinet, I want to see what its configuration is like and what kind of request size it's been optimized for. Now if it's been optimized for 64 megabyte transfer sizes and I'm trying to do 4 KB transfers, I may want to reconsider that drive configuration, unbind it and put it back to JBOD RAID 01 rather than sticking with the striping RAID 3 or RAID 5. Okay. So the S unit says what the stripe unit is, so that way I can ping the OS. I'm running on a RAID cabinet. The older days we'd actually have to hard code this stuff, but then the disk drives would change, or I'd end up in a different file system or on a different computer with a different type of disk drive geometry. So now I can simply ask or help the operating system with clues as to what the friendly I/O request size should be for that particular device. Again, I got to make sure that if it's lots of little I/O, can I up it first? I don't want to move a terabyte of data 1 byte at a time. Now, commands like RCP and CP and stuff in the past have been doing I/O transfers 16 KB at a time. So a lot of people with their home directories would mount the home directories with a 16 KB BIO size. But the newer CP commands and stuff, RCP have changed, FTP, they're doing 32 it looks like. So with PAR, I could run and see what my FTPs or CPs look like and then make sure that I'm efficient in using these buffers. So think of that as a fire bucket brigade. You're trying to pick the size of these things, and all depends upon, initially, what's the data characteristics like, and what's the record size like. I could have a large file with a small library buffer doing lots of little I/O, or I could have a small file in a large library buffer, and I don't fill it up all the way. When you fill up this fire bucket, you want to fill it up all the way, and you want it to be a whole friendly multiple number of the common denominator for this whole fire bucket brigade. And that includes the hardware caches that go on in here too. So in the video market, they make it a few large pages, and in the database market, they make it lots of little pages. Unfortunately, you don't have as much flexibility at the size of the pages. You get a 512 kbyte online or on-disk cache, and you can go 1 to 7 in terms of number of pages to break that up into. It's not as flexible as like an LD cache command was to set number of pages and size of each page in a very easy block configuration, 512 byte or 4 kbyte blocks. So that's I/O. Do you have a question, Mark? As I said before, memory is an I/O problem. When we run out of memory, we turn it into an I/O problem. But to finish this up, I need to go through the memory chapter that we have. We're down to our last half hour here, so. By the way, if you go off to my webpage, there is a good book here that documents a lot of what I've talked about this week as well. Bullet 15, the IRIX functional overview. This is another lecture class that gets into this and talks about, for example, on the memory management, we'll talk about all the different pieces. So this is a good book. Normally I want it as a pre-course, but nobody ever comes into this class with it as a pre-course. Talking about page tables and TLB buffers, what the TLB buffer looks like, things of that sort. So be aware of that manual. It's a good manual.
What is that?
It's called the IRIX Functional Overview, and it's a lecture class that I offer as well. And if you go to my home directory, let's see if I've got home here. It was the bullet number 15, the IRIX Overview class. IFO is what we call it. Also, we've got to do this now. We have a new online evaluation process. I need you to write this down. If I can even find it. I haven't even tried this myself yet. So you can do this afternoon or back from site. I do need to get feedback. And when you do get SAR data or accounting data questions, feel free to send me email. I'm usually not near the phone. Okay, so email is the better way to get me. Next year, it's like 3 weeks a month that I'm in a classroom, so what we've got here. Serve info, got Americas. And it's APUS/SE_IN_CTR_.
Now, we've talked a little bit about memory. I'm just going to go through the pieces that we have in the workbook. The main thing that we really need to talk about is SAR-P and SAR-W. But just about every day this week, we've dealt with memory issues. Now, you were asking at the beginning of the week, how do I tell them how to set swap? I like to say as much as you need for your workload, but don't swap. In other words, if I'm a 96 megabyte O2, and I'm trying to run Adobe Premiere needs more than 96 meg. I'd rather have them buy more memory than deal with the swapping. You don't need any swap at all. You can run without swap. It's just that if you do add more and more swap, that means more and more I/O traffic to that swap device, and that would be bad. People used to set swap based upon some sort of ratio of workload to physical memory, but those ratios don't make sense anymore either.
Let me bookmark this.